Modern artificial intelligence routinely projects the illusion of deep domain expertise. We input complex queries and receive highly structured, articulate responses. But beneath the surface, these models rely on shallow statistical pattern matching across vast training datasets, guessing the next logical word rather than actually thinking. This line chart plots model performance on the massive multitask language understanding test over time. In 2021, top models scored under 50%. By 2024, they hit a ceiling above 90%. This is benchmark saturation. The tests we built to measure intelligence were maxed out. When top models began effortlessly passing the SAT and the Uniform Bar exam, industry leaders concluded that traditional tests had become obsolete. The models had simply absorbed the test patterns during training. To find the true limits of these systems, researchers designed the GPQA Diamond benchmark. This is a gauntlet of 198 PhD-level questions spanning biology, physics, and chemistry, specifically engineered to stump highly skilled human-mon experts. The telemetry from this new benchmark initially looked promising. Frontier models like Gemini 3 Pro and GPT-5 currently score up to 94%. On paper, this implies they have achieved absolute parity with human scientific experts. However, these scores are deceptive. The GPQA Diamond relies heavily on multiple-choice formats. By structuring the test this way, the benchmark still rewards advanced heuristics and process of elimination guessing, rather than forcing the model to generate step-by-step logic from scratch. As long as an architecture can guess its way to a high score through context clues, statistical fluency will be mistaken for genuine domain expertise. Exposing the real limitations of these models requires a radically different type of stress test. That test is Humanities Last Exam, or HLE. It consists of 2,500 closed-ended, multimodal graduate questions that require exact match answers. Crucially, the dataset is heavily vetted to ensure the answers cannot be memorized from a quick web search. There are absolutely no multiple-choice safety nets. This bar chart places the 94% GPQA score next to the 90% human baseline. But plotted against Humanities Last Exam, performance drops to 37.5%. The collapse is severe in multimodal questions. Forced to synthesize text with schematics, prediction mechanisms break down. Worse, models lack awareness of their own failure. During HLE testing, AI systems exhibit severe confidence calibration errors, routinely assigning near 100% certainty to answers that are completely mathematically incorrect. This poor calibration carries massive real-world implications. In high-stakes fields like clinical healthcare or structural engineering, an AI delivering a factual error with absolute certainty turns a simple mistake into highly dangerous misinformation. Statistical next token prediction cannot brute force its way through true deductive logic. To cross this deduction gap, researchers are moving away from standard direct response models in favor of large reasoning models. This standard language model policy emits a final answer, Y, directly from the prompt, X, outputting immediately. Large reasoning models alter this. We expand the equation to include an intermediate reasoning trace, Z, generating an explicit chain of thought before the final output. Building this architecture begins with supervised fine-tuning. Engineers train the base model on vast datasets of human-annotated or AI-distilled reasoning traces, teaching it the syntax of step-by-step problem-solving. This flowchart illustrates the next critical phase, reinforcement learning. Supervised fine-tuning alone is insufficient. The optimization loop must split rewards into two distinct categories: outcome rewards that evaluate the final answer, and process rewards that evaluate the intermediate steps. By applying process rewards, the system forces the model to evaluate the structural logic of its own intermediate steps. It is penalized for logical leaps and rewarded for sound deductions, rather than just getting lucky with the final outcome. Externalizing these cognitive steps and assigning rewards directly to the process allows LRMs to achieve state-of-the-art accuracy in highly structured mathematical and coding domains. But forcing a model to think out loud introduces entirely new structural flaws. We can observe these structural flaws by applying an LRM to a specific test case, the rod and tension physics problem from Humanities Last Exam. It is a multi-step mechanics puzzle requiring energy and motion constraint calculations. As the model generates its chain of thought, researchers map the raw text into a finite state machine. This dynamic reasoning graph translates paragraphs of text into distinct cognitive episodes, moving between states like analyze, plan, deduce, backtrack, and verify. Mapping the trace exposes the first major pathology, overthinking. The reward system inadvertently trains models to seek process validation over conclusion. The reasoning graph forms excessively long, cyclical loops, trapping the model in endless backtracking that degrades accuracy rather than improving it. Conversely, these traces suffer from extreme brittleness. If perceptual uncertainty or a confounder is introduced, the deductive chain collapses, reverting the model to random guessing. These extended traces also reveal a hidden threat: latent, unsafe reasoning. In a standard model, the path from prompt to answer is direct. But because LRMs generate thousands of tokens of internal thought across an expanded sequence of intermediate steps, they create a massive attack surface where harmful or illicit logic can manifest and remain hidden from the final output. These harmful intermediate steps can exist independently of the conclusion. The final output presented to the user might appear completely benign, while the logic used to reach it relies on highly unsafe computations. Chain of thought traces create a dilemma of transparent opacity. The reasoning process is suddenly visible to engineers, but it proves to be highly unstable and dangerously misaligned. Securing these models requires new intervention techniques entirely. Historically, the industry attempted to solve black box opacity by applying post hoc interpretability frameworks. These are autopsy tools used to examine static models after a decision has already been made. This conceptual visualization shows Shapley additive explanations, or SHAP. It uses cooperative game theory to calculate the exact mathematical contribution of each input feature, determining exactly how the removal of specific data points shifts a model's final prediction score. Another framework is LIME, which draws a localized, interpretable boundary around a single opaque prediction. It builds a simplified surrogate model near the data point to guess the primary model's underlying intent. These static tools cannot monitor a live, multi-step autoregressive reasoning trace as it happens. They can explain a decision after the fact, but they lack the mechanism to stop a model from generating harmful logic in real time. To mitigate risks in an active chain of thought, researchers use intervened preference optimization, or IPO. When it detects an unsafe compliance queue, it swaps it for a safety trigger node, forcing the model to recalculate a safe downstream pathway. True LRM alignment requires abandoning postmortem analysis. By instituting real-time algorithmic interventions, developers can mathematically collapse the probability of downstream harm occurring during the reasoning phase itself. Governing the logic is only half the battle. The other is scaling it. Running LRMs in production incurs an extreme computational cost. Forcing a model to generate deliberative reasoning traces can increase inference overhead by up to 250%. To solve the overthinking pathology and the latency bottleneck simultaneously, engineers deploy a technique known as adaptive compute, or fast-slow decoding. This performance graph illustrates adaptive reasoning suppression. The system actively monitors the model's internal certainty thresholds at multiple checkpoints. Once mathematical confidence peaks, the threshold cuts off the trace early, saving up to 53% in compute overhead without sacrificing accuracy. Deploying these technical safeguards has moved beyond engineering optimization and into the realm of legal necessity. Under the European Union's AI Act, major AI systems must now provide a clear, interpretable basis for their decisions, which brings us back to the central tension of humanity's last exam. Today, the most advanced large reasoning models top out at roughly 37.5%. The human expert baseline sits at 90%. Feeding more raw data into these systems will not close this gap. The limitations constraining artificial intelligence are no longer based on the volume of training data, but on the structural limitations of the architecture itself. Closing the 50-point gap on humanity's last exam depends on structural and architectural evolution. success requires a precise balance of process-reward reinforcement, adaptive compute efficiency, and intrinsic mathematical interpretability to build systems that actually deduce knowledge.